So last day we did a bit of live coding, and in particular we saw how the game of nim could be implemented in Haskell. So what we're going to be doing today is our final lecture on the course, and the background to this is that up until this point we've been thinking about writing programs which are clear, concise and correct. It's the 3 C's which we have mentioned many times. But what we haven't really thought about so far is how Haskell programs are actually executed. So that's what we're going to be thinking about today, and in particular we're going to be looking at what's known as lazy evaluation. So the introduction to today's class is that expressions in Haskell are evaluated using a simple technique which is called lazy evaluation. And we'll come to what this actually is shortly, but before we do that, I just want to give you 4 key benefits which we will find from this technique. So the first of the benefits is that lazy evaluation avoids doing unnecessary work, or it avoids doing unnecessary evaluation. And this is really why the technique is called lazy evaluation, because it doesn't do any work unless it's absolutely necessary in order to produce the final result. And of course, this can also make your programs potentially more efficient. The second benefit is that lazy evaluation ensures termination whenever possible. So if there's any possible way that your program could be executed or evaluated to ensure that it actually terminates with the final result, then lazy evaluation will do that for you. So this is a very nice desirable property. It ensures termination whenever possible. So the third advantage, or the third benefit, is something we've seen a little bit of already in the course. Lazy evaluation supports programming with infinite lists, and actually more generally than this, it supports programming with infinite structures. So if you haven't seen lazy evaluation before, this sounds like something which is maybe impossible, but actually we'll see laziness allows you to do this in a very clean and simple way. And the final benefit, which we'll see today, is that lazy evaluation also allows your programs to be more modular. And in particular, it's going to allow you to separate the control part of a program from the data part of a program. And this is something which you really can't do in other languages which don't support lazy evaluation. So again, we're going to see some examples of that today. So to kick things off, we're going to look at the most basic way of evaluating expressions. And this is something you're already familiar with from high school maths, and it's the idea of simply applying definitions until no further simplification is possible. So we're going to have a little example of this, which we're going to look at over the next 2 slides. So what I've done at the top is I've defined a little function called square, and square simply takes a number n and returns you n times n. And then what we're going to look at is a simple example of an expression which we can try to evaluate. So in this case, the expression I've chosen is square of 1 plus 2. So you can ask yourself, how do you evaluate this? Well, you evaluate it just by applying definitions until no further simplification is possible. So what I could do first is I could choose to apply the plus operator. So I could do the 1 plus 2, and that would give me the 3. And then I could apply the squaring operator. So I could say that square of n is n times n. So I'll get 3 times 3. And then finally, I could apply the multiplication operator. So this is a completely straightforward idea. We're starting with an expression, square of 1 plus 2, and we're just applying definitions until no further simplification is possible. However, this is not the only way that we could have evaluated this particular example. So let's see the other possible evaluation order. So what we did on the previous slide is we did the addition first, but we could also do the squaring first, because square of n is simply n times n. So in this case, n is 1 plus 2. So if I apply the squaring function, I'm going to get 1 plus 2 times 1 plus 2. And then of course now I can simplify further by applying definitions. I can do the first addition, 1 plus 2 to get 3. Then I can do the second addition, 1 plus 2 to get 3. And then finally I can do the multiplication and I am done. And the important point here is the point at the bottom of the slide. In Haskell, any way of evaluating the same expression will always give the same result, provided that it terminates. So we saw two different ways of evaluating square of 1 plus 2. The first time around we did the addition first and we got the result 9. The second time around on this slide we did the squaring function first, but we still got the same result. And this is one of the important facts that we're going to be learning today. So any way of evaluating the same expression in a pure functional language such as Haskell will give the same result, provided that it terminates. So this leads us on now, very naturally, to the question of evaluation strategies. Because if every possible way of evaluating an expression in Haskell is always going to give the same result, provided that it terminates, how do we choose what to do next? So it turns out that there's two main strategies for deciding which reducible expression, or regex as it's called for short, to consider next. And these are two kind of extreme strategies. So the first of these is where we choose a reducible expression, or regex, which is innermost. And this is a very simple and intuitive idea, but if you wanted to be formal about it, you could say an innermost regex is one that does not contain another regex. So it's as small as possible. And then the other approach is the other extreme. You choose a reducible expression, or regex, which is outermost. And again, this is a very intuitive concept, but if you want it to be formal, an outermost regex is one that is not contained in another reducible expression. So it's as big as possible. So innermost and outermost are the two most common evaluation strategies. So we can ask ourselves, how do these actually compare? So what we're going to do is compare them along a number of different axes. So the first thing we're going to think about is how these two evaluation strategies differ in terms of their termination behavior. And in order to do this, we're going to consider the simple recursive definition at the top of the slide. What I'm defining here is infinity to be 1 plus infinity. And this is a perfectly well-defined value in a language such as Haskell. And if you expanded the definition out, you would simply see that infinity is 1 plus 1 plus 1 forever. Basically, it's the way you represent infinity as a simple recursive definition. And then what we can do is we can consider the example in the middle blue box on the slide. So FST is a library function. It's usually pronounced first, and what it does is it takes a pair of things and it gives you back the first thing in the pair. So in this case, we're computing the result of applying first to the pair comprising 0 and infinity. So what we can do now is imagine evaluating this expression using these two extreme evaluation strategies, innermost and outermost. So we'll do innermost first. So innermost evaluation, it's very easy to see what to do here. We can simply expand out the definition of infinity because that's the innermost thing which we can actually expand. So if we expand the infinity, we're going to get 1 plus infinity. And then we think, well, what's the innermost thing we can do now? Well, again, it's simply expanding the infinity. So if we expand it again, we get another 1 plus infinity, and you see what's happening here. Every time when we apply innermost evaluation, we would expand infinity one step further, so the expression will get larger and larger. So the conclusion here is that if we evaluate this expression using innermost evaluation, it won't terminate. It will just get larger and larger forever. And this is in contrast to if we evaluate this expression using outermost evaluation. So the definition for first says the first component of a pair xy is simply going to be the x. So if we applied the first function to the pair comprising 0 and infinity, and we evaluate this using outermost evaluation, we can immediately just apply the first function, and in one step we get termination and we get the result 0. So there's a couple of points to note about this example. So the first point is something we've essentially just proved by example. Outermost evaluation may give a result when innermost evaluation fails to terminate. So we saw if you applied first to 0 and infinity, with innermost evaluation, it didn't terminate. The expression just got larger and larger forever. Whereas with outermost reduction, as we see at the top of the slide here, it terminates in one step. And then what we have at the bottom of the slide is another one of these little facts about Haskell, which we're going to be seeing today. And this is a nice one. If any evaluation sequence terminates, then so does outermost evaluation, and it will give you the same result. So this is a very nice property. It's saying that if there's any possible way to find an evaluation path through your expression or through your program, then outermost evaluation will find a way to make it terminate as well, with the same result. So at the moment, it sounds like outermost evaluation is a clear winner, or the clear winner. So you can ask yourself, well, what's the catch? So the catch is in the number of reduction steps that may be required. So to illustrate this, we're going to go back to the original example which we looked at today, which was square of 1 plus 2. And I showed you two different ways that you could evaluate this, and in fact the first one was innermost evaluation and the second one was outermost evaluation. So we're going to revisit these now and think about the number of reduction steps. So on the left hand side we're doing innermost evaluation, so we can apply the inner plus first of all and we'll get square of 3. Then we can apply the squaring function and we get 3 times 3. Then we can apply the multiply function and then we finally get the result 9. So in this case, what we see is their innermost evaluation takes 3 steps to terminate. Then what we have on the right hand side is our second example, which was actually using outermost evaluation. So that time around we applied the squaring function first, so we get 1 plus 2 times 1 plus 2. Then we did the first addition, then we did the second addition, and then finally we did the multiplication and we got back the result 9. And of course this time around we actually took 4 steps. And the reason we took 4 steps is we actually duplicated the argument 1 plus 2 and then evaluated it twice. So there's a number of points to note about this example. So the first point is that the outermost version is inefficient because the argument 1 plus 2 was duplicated when the square function was applied, and hence it was evaluated twice. And more generally, due to this kind of duplication, outermost evaluation may require more steps than innermost. But there's a very simple fix to this, and it's a kind of very obvious fix as well. This problem can easily be avoided by using pointers to indicate sharing of arguments. So in particular, rather than duplicating something like 1 plus 2 when we applied the definition of the squaring function, we could just keep one copy of that parameter but share it using pointers. So I can give you a simple example of how you might do something like this in practice. So here we're evaluating square of 1 plus 2, and we're going to apply the squaring function first, but this time we're not going to copy the 1 plus 2 or duplicate it. We will keep only one copy of the 1 plus 2 and we'll share it via these two little pointers. And then in the next step, when we evaluate the 1 plus 2 to get 3, these two pointers will be sharing that evaluated result 3, so that finally we can get the result 9, which means we have evaluated the square of 1 plus 2 in 3 steps now, just like we did with innermost evaluation. And just to kind of emphasize the point here, the shared argument 1 plus 2 is now only evaluated once. So this actually gives us a new evaluation strategy, and this is what lazy evaluation is. Lazy evaluation is simply outermost evaluation plus sharing of arguments in the way that we've just seen. So if I asked you in a Haskell exam, what is lazy evaluation? You just say lazy evaluation is outermost evaluation combined with the idea of sharing arguments. And one more little point to note down the bottom here, lazy evaluation ensures termination whenever possible, but it never requires more steps than innermost evaluation, and it sometimes requires fewer, in particular because innermost evaluation may require an infinite number of steps and thereby not actually terminate. So the next thing we're going to think about now is how different evaluation strategies compare in terms of infinite lists. So what I've done at the top of the slide here is I've defined the infinite list of ones via a simple recursive definition. So the equation simply says ones is a single one followed by ones. So it's a recursive one-line definition. So if we go to the example now and we think about how do you evaluate ones, well, in this case, it doesn't matter what evaluation strategy you actually use, because at each point in the evaluation, there's only one thing which you can expand, which is the definition of ones. So if we expand ones, we get 1 followed by ones, and then we expand ones again, and we get another one, then we expand ones again, and we get a third one. And of course, this can go on forever. And in this manner, you see that the equation at the top of the slide here represents an infinite list of ones. So now we can imagine or think about what happens if we try and select the first element from the infinite list of ones. And we can do this using our old friend, the head function. So remember, head takes a non-empty list and gives us back the first element in the list. So what we're going to do is we're going to have two examples here. We're going to evaluate head of ones using innermost evaluation. And on the right hand side, we're going to evaluate head of ones using lazy evaluation. Or in fact, this is just going to be equivalent to outermost here because we're not using any sharing. So if we go to the innermost side first of all, on the left, what's the innermost thing that we could do? Well, we could expand out the definition of ones. And then we get down to head of 1 followed by ones. And of course, you can see what's going to happen here. We just expand the definition of ones again. And this is basically going to go on forever. And this will not terminate. So what we see is if we try and select the first element of the infinite list of ones by using the head function, if we do that using innermost evaluation, then evaluation does not terminate. It simply goes on forever. So now we can move across to the right hand side where we're using lazy evaluation, or actually again outermost evaluation, because we're not using any sharing of arguments here. So what can we do this time around? Well, we can't apply the head function first because we don't know. We have a non-empty list at this point. So we need to expand the definition of ones. So now we have head of 1 followed by ones, and now we can apply the definition of the head function. That's the outermost thing that we can do. So we apply the head function and we'll simply get back the value 1. And this time, rather than going into an infinite loop and not terminating, as we did on the left-hand side with innermost evaluation, using lazy evaluation or outermost evaluation, this actually terminates in 2 steps, which is great. So as usual, we've got a number of points to note here. So the first one is that in the lazy or outermost case, only the first element of the list ones is actually produced, as the rest of the list is not actually required. And this is where we get the name lazy evaluation from. So in general, with lazy evaluation, expressions are only evaluated as much as required by the context in which they are used. So in this particular example, we had the infinite list ones, but the context was the head function that says we are only interested in the first value in that list. So the list ones only gets evaluated as much as required by the head function, which means we only actually need to produce the first value. So an important point is the one down the bottom here. What we see now is that when we define the infinite list of ones by ones equals 1 colon ones, it's not actually an infinite list, it's a potentially infinite list, and it will only get evaluated as much as required by the context in which it's used. So this brings us now to one of the key advantages of lazy evaluation, which is that it supports a new form of modular programming. And the idea is very, very simple. So lazy evaluation allows us to make programs more modular by separating control from data. So to see what this actually means, we can look at this simple example in the blue box here. So here what we're doing is we're applying the take function to the number 5 and the list ones. And what, remember, the take function does is you give it a number like 5, you give it a list like ones, and it consumes that number of elements from the start of the list. So in this case, we just get a finite list comprising 5 ones. But the interesting thing here is that we've been able to make this computation of generating 5 ones more modular because we've separated the control part from the data part. So what we see in the callout box at the bottom is the data part, which is ones, or the infinite list of ones, or the potentially infinite list of ones, as we now know it is, that's only evaluated as much as required by the context in which it's used, which is the control part take 5. So we've been able to separate the idea of generating 5 ones into a data part, which is a potentially infinite list of ones, and then a control part, take 5, which says how many elements we actually want from that potentially infinite list. If we didn't have lazy evaluation at our disposal, the control and data parts would need to be combined into one. And this is exactly what the replicate function does in the standard library. So if we look at the little example down at the bottom, replicate 5 of 1 just gives us 5 copies of 1. So I won't go through the actual definition of the replicate function here. It's an entirely straightforward, simple recursive definition, and it's by recursion on the first parameter. But the point here is that if I was going to generate 5 copies of 1, I think it's cleaner to have an infinite list of ones and then take the first 5, because then I've separated my control part from my data part. I think it's cleaner to do it like that rather than to actually have a definition for a replicate function like this. And in fact, if you look in the definition for a replicate in the standard library, it's not actually defined in this combined form using recursion. It's actually defined by exploiting this idea of separating control and data. So the actual definition for replicate is replicate nx is take of n applied to repeat of x. And repeat of x produces a potentially infinite list of copies of x, and then the take n is going to select the first n of those. So to wrap things up now, what I'd like to give you is a simple example of modular programming with infinite lists. And what we're actually going to be looking at is generating prime numbers. And you may remember, right back at the start of the course, I think it was in lecture 5, I gave you a simple list comprehension approach to generating prime numbers. But actually what we're going to see today is how to generate the infinite sequence of all prime numbers by exploiting the power of lazy evaluation. And the program which we're going to be writing here is actually going to be more efficient than the simple version that we wrote using list comprehensions in lecture 5. So what I've given you on the slide here is a 4-step process for generating the infinite sequence of all prime numbers. And some of you have probably seen this process before. It's very famous. It's called the sieve of Eratosthenes. And Eratosthenes was a Greek mathematician who was the first person to describe this process. So the process is very simple. So in the first step, we write down the infinite sequence of all numbers beginning with 2. So we write down 2, 3, 4, etc. In the second step, we're going to mark the first number in that sequence, which we're going to call p, as being a prime number. So initially, the sequence will be 2, 3, 4, etc. So we'll mark the first number, 2, as being a prime number. Then in the third step, we simply delete all the multiples of p from the sequence. So initially we would delete all the multiples of 2 from the sequence, and then in the fourth step we just go back to step 2 and repeat and repeat. So infinity actually occurs in a number of places in this algorithm. So in particular, it occurs in the first step because we're writing down the infinite sequence, 2, 3, 4, etc. It occurs in the third step because we're deleting an infinite number of multiples from an infinite sequence. And finally, it also occurs in the fourth step because we're repeating the process an infinite number of times. So we have this simple four-step process, the sieve of Eratosthenes. Let's have a simple example to see how it actually works in practice. So what I've done on the slide here is built a simple animation. So the first step is that we write down the infinite sequence beginning with 2. So unfortunately, I don't have an infinite slide here, so I've only written down the first 12 numbers, but in principle, this sequence here goes on forever. So that's the first step. Then in the second step, we mark the first value in the sequence as being prime. So I'm going to mark the first value, 2, as being a prime number. I'll indicate that by yellow, and that's how we're going to indicate all of the prime numbers. These are going to be the yellow numbers. Then in step 3, we remove all multiples of 2 from the sequence. So the way I'm going to represent this is by a sieving-like process. I'm going to imagine putting a little barrier under each of the multiples of 2. So I put a barrier under the 2, the 4, and the 6, and so on. And then I'm going to imagine the numbers kind of falling down the screen, and those that hit the barrier are kind of sieved out. Okay, so we get the numbers 3, 5, 7, 9, and 11 remaining. And then we simply go back to the second step. We mark the first value in the sequence as being prime, so that number is now 3. Then we're going to remove all the multiples of 3 from the sequence. So we put a little barrier under the 3, under the 6, which is already gone. We put a barrier under the 9 and the 12 and so on. And then we imagine, again, the numbers falling down the screen, and the multiples of 3 get sieved out, and we get left with 5, 7, 11, and so on. Then we go back to the second step. We mark the first value, in this case now 5, as being a prime number, and then we're going to put a little barrier under all the multiples of 5, so the 5 and the 10, and so on. The numbers fall down, we get left with 7 and 11, and so on. 7 is now prime. We filter out all the multiples of 7, the numbers fall down, 11 is marked as prime, and we filter out all the multiples of 11 and so on. So what we see is that just by following this process, we have produced the first 5 prime numbers in yellow. We have 2, 3, 5, 7, and 11, but this is an infinite process. We can carry it on as long as we like, and we can produce the infinite sequence of all prime numbers. So now we've seen how to generate the infinite sequence of prime numbers using the sieve of Eratosthenes. So what I've done is I've swapped over to my machine now, and we're going to see how to implement this in Haskell. And actually, as we'll see, it's a very natural, just kind of direct translation of the 4-step algorithm into code, and we're actually going to end up with a 2-line program which implements the sieve of Eratosthenes. So let me start up a text editor. And let me call it primes.hs, make a little bit of space here. And what I'm going to do is define an infinite list, or rather a potentially infinite list, of all the prime numbers, and I'm going to do it by sieving the infinite list starting from 2. So what we see here is we have the first step in the algorithm, which was write down all the numbers from 2, 3, 4, etc. up to infinity. So what we have there in the blue box is the potentially infinite list beginning with 2. So that's the first step of the process. And what I'm doing then here is I'm passing it into a helper function called sieve, and we're going to write that now, and that's going to implement steps 2, 3, and 4 of the process. So let me write down the definition for the sieve function first of all, and then I will explain how it works. So it's just one line long. Mod xp does not equal 0. So this is the complete implementation of the sieve of Eratosthenes now. So how does it actually work? So the sieve function is going to implement steps 2, 3, and 4. And you see it's matching on a non-empty list here. P is the first value in the list, and X's is everything else in the list. So what we're going to do then on the right hand side is, first of all, we're going to output the first value P in the sequence. Okay, so that corresponds to marking the first value P as being a prime number. So this is step 2. Then what we have in the brackets over here is a list comprehension which implements step 3. And step 3 was remove all multiples of p from the remaining list of numbers. So all we're doing here is we're running over the list. So we have a simple generator, x is drawn from x's, and then we have a simple guard that says when you take the remainder of dividing x by p, it should not be 0. So the entire effect of this list comprehension is to remove all multiples of p from the sequence. So initially when p is 2, because we're passing in this list up here, so the p will be 2, we'll keep the 2, and then we'll remove, in this list comprehension, all multiples of 2 from the list. So that implements step 3. And then the final step, step 4, is to go back to step 2. So all we do is we call the sieve function recursively again on that particular list, because sieve implements steps 2, 3, and 4. So again, this is just a 2-line program which implements the sieve of Eratosthenes in a very, very simple manner. Here we have step 1, we write down all the numbers from 2 up to infinity. Step 2 is we mark the value p as being prime. Step 3 is we remove all multiples of p from the sequence. And then step 4 is we go back to step 2. So let me save this file. And now we can run it down below. So if I do ghci primes.hs, it's loaded in, no problems, that's excellent. So now I can print out, if I wish, the infinite list of all prime numbers. And of course, this is going to go on forever, and it starts off quite quickly, but as you get to larger numbers, it's going to get slower and slower. But it is much faster than the simple version that we wrote back in lecture 5. So let me just interrupt this now. But the interesting thing about this, and this is the idea of modular programming, I can now use this infinite list of primes as data, and I can implement different control paths to decide how many prime numbers I'm actually interested in generating. So for example, if I didn't want the infinite list of all primes, if I just wanted the first 10 primes, I could say take 10 primes. And what I'll get then is the first 10 prime numbers. So again, this is this idea of modular programming. It's separating the data part, in this case the infinite list or potentially infinite list of all prime numbers, from the control part, which in this case is simply selecting the first 10 prime numbers. And what will happen is that lazy evaluation, it will kind of collaborate between the two parts here, and you'll only generate the first 10 prime numbers, and then it will stop. So again, an example of this idea of modular programming. So let me give you another example, because we could have a different control part. We could say take while less than 20 of primes. And again, here we have our data part, which is an infinite list of prime numbers. Here we have a different control part. And what we're doing this time is we're selecting elements from the infinite list of prime numbers until one is bigger than 20. Okay, or 20 or more. So this is going to give us all the prime numbers which are less than 20. So again, the idea separating data from control, and you can have different control parts depending on what you actually want to do with the data. So to wrap things up now, I'd actually like to show you one more interesting example to do with prime numbers. And it's the idea of twin primes. So twin primes are prime numbers which differ by precisely 2. So for example, 3 and 5 are both prime numbers and they differ by 2. So those are twin primes. And similarly, 17 and 19, those are both prime numbers and they differ by precisely 2. And these are twin primes. So we can think, how can we write a Haskell program which generates the list of twin prime numbers? So this actually turns out to also be very easy to do. So what I'm going to do up at the top here is I'm going to define a little function called twin. And what twin does is you give it a pair of numbers x and y, and it's going to decide if they differ by precisely 2. So if y equals x plus 2, then I'm going to say that these two numbers are twins. So for example, if I go down here, reload the file, and I say is 3 and 5 a twin, it will say yes, because they are 2 apart. Whereas if I say is 7 and 11 a twin, those are not 2 apart, so I get false. And now it's actually very easy to generate twin primes because I can just define a very simple one-line definition. Let me again just write this down and then I'll explain how it works. So here is the one-line program to generate an infinite list or potentially infinite list of all twin prime numbers. So it's interesting how it's actually working. So what I'm doing in the brackets here is I'm first of all zipping the infinite list of prime numbers with the tail of that list. So the effective zip is, remember, it takes two lists and it pairs up the corresponding elements. So it pairs up the first elements, the second elements, the third elements, and so on. So this is actually an infinite zip because we're zipping the infinite list of all prime numbers with the infinite list of all prime numbers apart from the first one. So the effect of this zip, the stuff in the brackets here, is basically going to pair each prime number with the next prime number. So you get 2 paired with 3, 3 paired with 5, 5 paired with 7, and so on. And then all we're going to do is we're going to filter the pairs from that list which are actually twins. Okay, so this is a nice one-line program which will generate the infinite list of all twin primes. So let's just test that this actually works. So I can type twins down here, or actually reload it first, type twins, and this will print out twin prime numbers for me. And it's actually unknown whether this is an infinite list or not. If you look on the Wikipedia page for twin primes, it's an unsolved problem in mathematics whether the list of all twin primes is actually infinite. But if it is an infinite list, this one-line program up here will actually find it for me. But again, because we're working in a lazy language, we can implement the idea of modular programming. If I just wanted, for example, the first 5 twin primes, I could just say take 5 of twins, and then I get the list down here of the first 5 twin prime numbers. So that's basically it for today. Normally at this point I would say see you again next time, but actually I won't see you again next time because this is the last lecture of the Haskell course. And I hope you've all enjoyed learning some basic Haskell with me this year. It's been really great to teach you in this kind of unusual way using YouTube videos. But if you have enjoyed learning the Haskell, remember that I do teach an advanced course in second year, so there's an opportunity to see more then.